analog electronics. Every year in gate examination, analog electronics has weightage around 8 to 12 marks. So it becomes a very important subject from the weightage point of view. Out of 55 technical questions, there will be around 6 to 7 questions from analog electronics. So uh, this is a very important subject for as far as gate examination is concerned. We'll start the subject with operational amplifier. Operational amplifier. An operational amplifier is basically an amplifier which amplifies the difference in the voltages applied at the input terminals. It basically has two inputs, one represented with positive sign known as non-inverting input, while other input represented with negative sign known as inverting input, and has an output terminal where a voltage is generated which is amplified version of the difference in the voltages applied at the input, which is equal to AOL, called as open loop gain of the amplifier multiplied with difference in the input voltages. Apart from this, we will have two more terminals. One is positive supply plus VCC, negative supply minus VEE. So this is a basic circuit representation of an operational amplifier. In the circuits we will use this symbol. An operational amplifier uh, has given this name because this operational amplifier is used not alone with some additional component, passive components. This can be used for some operations, mathematical operations like addition, subtraction, log, multiplication. These operations can be performed using this operational amplifier, means circuits can be designed using this operational amplifier for performing these mathematical operations. So as it can perform these mathematical operations, it is called operational amplifier. So we have already discussed that if we apply two voltages at the input, V1 voltage at the inverting input, V2 voltage at the non-inverting input, and it generates an output which is equal to AOL, open loop gain, into V2 minus V1. Basically it amplifies the difference in the voltages applied at the input. So if we have V2 greater than V1, then from this equation we can say that this difference will be positive. If this difference is positive, then output V0 will be positive. So an operational amplifier will generate a positive voltage at the output if the voltage at non-inverting input is greater than voltage at inverting input V1. If we have second case that V1 is greater than V2, if V1 is greater than V2, then this difference will be negative. If this difference is negative, voltage output V0 will be equal to negative. If this voltage is negative, we will say that if voltage at inverting input is greater than voltage at a non-inverting input, an operational amplifier will generate a negative voltage. Now we'll see some characteristics of operational amplifier which will be useful while analyzing the circuits. Characteristics of operational amplifier. Operational amplifier, uh, it is also written as op-amp. Operational amplifier. Characteristics. First important characteristics is open loop gain is around 10 raised to power 6 for an operational amplifier. Practically it is 10 raised to power 6, and ideally it is infinite. So first characteristics is that open loop gain AOL is equal to 10 raised to power 6, or ideally it is infinite. So it has a very high open loop gain. Next, input resistance is around 10 raised to power 6 ohm, and ideally it is infinite. Suppose this is an operational amplifier. If we have applied a voltage at this terminal, then the current will be I. This is voltage V. From this terminal, the input impedance Ri will be equal to V by I, and this input impedance is very high for this operational amplifier. If we apply a supply to this terminal, and this is voltage V and this is current I, then while seeing to this terminal, input impedance Ri will be equal to this voltage divided by this current. So the voltage divided by current will give the input resistance of op-amp, which is very high. Number 3, if input impedance are high, then the currents entering these two terminals, that is IB1 and IB2, are negligibly small. So third characteristics is that due to very high input resistance or input impedance, very high input impedance, IB1 and IB2 are negligibly small, and ideally they are 0. Ideally no current flows in the input terminals of op-amp because its input impedance is very high. Number 4, its output resistance or output impedance is very low, and ideally it is infinite. Ideally it is infinite. Apart from these characteristics, we will have two more characteristics about a CMRR and slew rate. These two characteristics we will see later uh, in this subject. Now, virtual ground concept. This virtual ground concept will be applicable only with negative feedback. So first we will see what is virtual ground concept, and we will use it when op-amp is applied with negative feedback. For example, this is an op-amp and these are the two voltages V1 and V2 applied at inverting and non-inverting terminal. It will generate an output which is equal to AOL into V2 minus V1. So it amplifies the difference in the input voltages. From this expression we will write as V2 minus V1 equal to V0 upon AOL. And we know that AOL is very high if it tends to infinity. AOL tends to infinity. V2 minus V1 will be equal to 0. That is V2 is equal to V1. So if one terminal is grounded, other terminal will be virtually grounded. So both the input terminals will be at same potential. This property will be seen only in negative feedback. When it is provided with negative feedback, the output make the difference in the input voltages nearly equal to 0. That is, both the input voltages are at same potential. This is virtual ground concept. Now we'll start analyzing the circuits using op-amp. First is inverting amplifier. Inverting amplifier. In this operational amplifier, uh, we have this output voltage V0, this resistance RF, this resistance R1, and this input. For some time I will deactivate this input source, so it will be grounded. And the voltage between these two resistances will be this voltage, which will be called as Vn, and this voltage will be called as Vp. So this voltage Vn. Now we can say that from the output, with the output, this network is connected, and this network has two resistances, and between these two resistances we have a terminal which is going to the input terminal of op-amp, which is going to inverting input of op-amp. So this is a negative feedback, and using this potential divider network, we are uh, giving feedback or from the output, some part of output which is divided by this potential divider network will be given at the input to the op-amp. So this is negative feedback. Using the characteristics, we will find the output voltage for this operational amplifier, which is an inverting amplifier. So first we know that Vp equal to 0 volt. It is clearly seen that Vp is grounded, so it will be equal to 0 volt. By virtual ground concept, we have Vn equal to Vp equal to 0 volt. Voltage at both the input terminals must be same. If one is 0 volt, other will be 0 volt. Now at this point Vn, we will apply KCL. For this KCL, we first write the currents at this connected in the branches connected to this node. There will be three branches, one going to the input, we have mark a current I1, one is going to the output, mark the current IF, and one going to the input of op-amp, mark the current is marked as IB. The direction of current can be taken as outward or inward, the result will be same, but we have to substitute the values of these currents accordingly, according to their direction. So next step is applying KCL at Vn. If we apply KCL at Vn point, from the Vn we can see that three currents are outgoing, there is no incoming current, and according to KCL equation, total outgoing current must be equal to total incoming current. Total outgoing current must be equal to total incoming current. Outgoing current are 3, I1, IF and IB, while there is no incoming current. Now I1 will be substituted. I1 is going in this direction, in this direction. So by seeing the direction, we will say that it is going from Vn to Vi. So it will be written as Vn minus Vi and divided by the resistances in between them, plus If. Direction is this. If this is the direction, this is going from Vn to V0. So it will be written as Vn minus V0 divided by Rf plus Ib. If we talk about Ib, then we know that input resistance of op-amp is very high and input current is 0. So Ib will be equal to 0. Now solving this equation, Vn equal to 0 volt, so minus Vi by Ri minus V0 by Rf equal to 0. Solving this equation, we get V0 equal to minus Rf upon R1 into Vi. In this expression, if we find ratio of V0 by Vi, it is equal to minus Rf upon R1, and this is called gain of inverting amplifier. Gain of inverting amplifier, and this negative sign represents 180 degrees phase shift. 180 degrees phase shift. If input is positive, then output will definitely be negative, because 180 degrees phase shift is provided by inverting amplifier. If input is negative, then output will be positive. This is the general expression for output of an inverting amplifier. Now the next circuit is non-inverting amplifier. Non-inverting amplifier. In the non-inverting amplifier, we will have slight modification. Again, there will be a negative feedback, but input will be given this time at non-inverting terminal VP VN. In this circuit, we can have this data that VP is equal to VI. If we apply virtual ground concept, so by virtual ground concept or virtual ground process, we have VP equal to VN equal to VI. Now again we will apply KCL at this point. There will be again three currents, IF, I1 and IB. Applying KCL at Vn. If we apply KCL at Vn, there will be three outgoing currents, IF, I1 and IB, and there will be no incoming current. Now substituting for all these three currents, I1 will be written as Vn minus 0 because this time it is grounded, divided by R1 plus IF. See the direction going from Vn to V0, Vn minus V0 divided by Rf plus IB will be 0 because no incoming current in op amp. Now we know that Vn equal to Vp. So substituting it, Vp upon R1 plus Vp upon Rf minus V0 upon Rf will be equal to 0. This will go this side. So Vp into 1 upon R1 plus 1 upon Rf will be equal to V0 by Rf. Cross multiplication we get R1 plus Rf upon R1 into Rf will be equal to V0 by Rf. This will be cancelled. So we get Vp into R1 plus Rf upon R1 equal to V0. Now this V0 can be written as R1 upon R1 plus Rf upon R1 into Vp. So we get 1 plus Rf upon R1 into Vp. This is the general expression for output of a non-inverting amplifier. So for non-inverting amplifier, the output equation V0 will be equal to 1 plus Rf upon R1 into Vp, voltage at non-inverting input. From this we can write V0 upon Vp will be equal to 1 plus Rf upon R1. This is the gain of non-inverting amplifier. Non-inverting amplifier. Gain of non-inverting amplifier. Positive gain represents that there is no phase shift provided by this non-inverting amplifier, and in this circuit we have Vp equal to Vi, so output can be written as 1 plus Rf upon R1 into Vi. Note that in every circuit this will not be the case. Vp sometimes may be different from Vi. Now we will have some modification in inverting amplifier, so we will see it as an example. So calculate the output for this circuit. This circuit is a non-inverting amplifier with slight difference. Difference is that this time Vp is not equal to Vi. There is some uh, network which divides Vi, means Vp is not equal to Vi. This is a non-inverting amplifier, and we know that for a non-inverting amplifier gain is 1 plus Rf upon R1. Gain is 1 plus Rf upon R1, and output is V naught equal to gain multiply voltage at non-inverting input Vp. Vp can be found out by solving this network which has resistance R2, R3 and voltage source Vi, and this end is grounded. This point has potential Vp. This potential Vp can be found out. This Vp will be equal to, according to potential division rule, equal to Vi into R2 upon R2 plus R3. So this can be substituted in this. We get V naught equal to 1 plus Rf upon R1 into R2 upon R2 plus R3 into Vi. This is the final expression for output of this circuit. Now take one more example. Calculate V naught. In this circuit we can see that it is uh, an inverting amplifier with slight modification. This time we have added this load resistance also. We have to calculate the output voltage V naught. So we will start our discussion. The analysis procedure will be same. Vp equal to 0 volt, Vn equal to Vp equal to 0 volt according to virtual ground concept. When we apply KCL at this point, we will have one current IF, one current I1, and we know that input current is 0. So when we apply KCL at Vn, we get I1 plus IF equal to 0. I1 is the current which is going in this direction, so we get Vn minus Vi upon R1 plus IF will be written as Vn minus V0 divided by Rf will be equal to 0, and we know that Vn equal to 0 volts, so minus Vi upon R1 minus V0 upon Rf equal to 0. So from this we get V0 equal to minus Rf upon R1 into Vi, which is the same expression as we got in an inverting amplifier. So now we can conclude that RL has no significance. It does not affect output of operational amplifier in of an inverting amplifier. Now next question, calculate V naught for the circuit. This voltage is Vn and this voltage is Vp. Again we have an inverting amplifier. So in this circuit we will start analyzing in the same way. Vp equal to 0 volt. If we use virtual ground concept, then according to virtual ground concept we have Vn equal to Vp equal to 0. So we know that this ground potential is 0 volt, and uh, now only we have shown that this voltage is also 0. Now as the potential on both the ends of this resistance are same, then the current through it I will be equal to 0. Now we will start our analysis in the same way. We will apply KCL at this point. There will be one current I1 through this resistance, there will be one current IF through this, and there will be one current I through this resistance R. Now total outgoing current will be I1 plus IF plus I will be equal to 0. Total incoming current, no incoming current. One more current will be there in the input terminal of op amp, and we have already shown that this current is 0. I1 will be written as V1 minus Vi divided by R1, plus If will be V1 minus V0 divided by Rf, plus V1 minus 0 divided by R equal to 0. We know that Vn equal to 0 volt, so minus Vi by R1 minus V0 by Rf, and if Vn is 0, this total term will be equal to 0. So from this expression we get V0 equal to minus Rf upon R1 into Vi. So this is the expression for output, and this time also we have got the same expression. So we can say that this resistance R has no effect on output, effect on in output V0. But this case is only in inverting amplifier. If we have non-inverting amplifier, then this resistance R will be counted in the circuit. So if inverting amplifier is there, we can neglect this resistance R, which is connected between inverting terminal and ground terminal. Now we will analyze a complex circuit. Calculate output voltage V0. Clearly seen that it is an inverting amplifier, and in this circuit we have to calculate V0. There is a complex network, this T network or star network in the feedback circuit. This circuit can be analyzed by converting the star network into its delta equivalent, and this circuit will look like this circuit. Now this star network, which has three resistances R R R, can be converted into a delta network. This resistance R dash will be the addition of these two resistances R plus R plus multiplication of these two resistances R into R divided by the opposite resistance R will be equal to 3R. Similarly, this R dash will be equal to 3R, this R dash will be equal to 3R. So all these resistances will be of value 3R. Now this circuit can be further simplified as this will be the resistance 3R, this will be the resistance 3R, and this will be the resistance 3R. This terminal is connected to output, so between output and ground there is a resistance 3R. Between output and ground there is a resistance 3R. Between VP and ground there is resistance 3R. Between VP and ground there is resistance 3R. Between VP and ground there is resistance 3R. This resistance is R1 and this is voltage VI. Now uh, in the two example two previous examples, we have already shown that in an inverting amplifier this resistance has no significance, and also this load resistance has no significance. So this circuit will be a simple inverting amplifier whose output V0 is equal to minus RF upon R1 into VI, which will be equal to minus 3R upon R1 into VI. So this will be final output of this circuit. Now we will see some a summing amplifier using op amp. This is an inverting amplifier. This circuit is called summing amplifier. It is an inverting amplifier basically. We can use non-inverting amplifier also. So in this circuit analysis would be same. VP equal to 0 volts, so VN equal to VP equal to will be 0 volts. Next we will apply KCL at Vn. If we apply KCL at Vn, we will mark all the currents. Suppose I mark this current as I1, this current as I2 and this current as IF. Note that there will be no effect on the calculation if I take the direction of current I1 and I2 as incoming current. The equation will be written as accordingly. There will be no effect on the calculation will be correct. So applying KCL at Vn, total incoming current should be equal to total outgoing current. This time I have taken two incoming currents, I1 and I2, while there is one outgoing current that is equal to IF. So I1 can be written as V1 minus Vn divided by R1. Note that I1 is substituted by seeing its direction. It is going from Vn to V1 to Vn, V1 to Vn divided by R1 plus I2. Direction is incoming, coming from V2 towards Vn divided by resistance R1 equal to IF can be substituted as Vn minus V0 divided by Rf. We know that Vn equal to 0 volt, so V1 upon R1 plus V2 upon R1 is equal to minus V0 upon Rf. So from this V0 can be written as minus Rf upon R1 into V1. Sorry, this is V2. V1 plus V2. So this is the general expression of a summing amplifier, inverting summing